Okay, welcome back to another one of my video log recording sessions where I talk about genetic algorithms and basic stuff, and hopefully I can move on to more advanced stuff, advanced topics. Yeah. Um, yeah. Well, uh, in this video I'll be covering the Jupyter Notebook file called Genetic Algorithm Grid Search 2 Rev, as in revised. Again, revised version, because I am, instead of calculating the average of top 30 key values in the entities dictionary within each generation, I am calculating the average of top n%, for example 10% entities, in terms of their summed utility values. And so obviously this will take into account how many entities there are per summed utility value, or per key, in terms of entities dictionary, in in every generation. So in my last video I left off with a brief look at this notebook, but decided that I decided that I wouldn't use that version of the notebook because I didn't have pictures that were good enough, or pictures, plots with the right lines, with the right squiggly values. So in this notebook I re-illustrated those plots. Well, reran the plots. And so the date is 2025 March 19th, and I'm not going to run this notebook on Google Colab because it will just take too much time. So getting started, again I have 20 items, 20 values, and 20 constraint values, as in physical weight. The rest are the same as in the previous video. However, in this notebook I try to assess the impact that number of entities in the population, or within each population per generation, whatever, has on the evolution and effectiveness of entity generation with population of null entities, void genes, 0, 0, 0, 0, zeros, entities full of zeros. So all these go through the same procedures, and we do it again. Here in this case, if we look at the hyperparameters cell, the initial population is 50. So for these number 1, 2, 3, and 3, it's most likely to be, the population is most likely to be just 50. So keeping that in mind, this is what happens. Is it 50? Let me just check. Assessment. Yeah, I think it's 50. Yeah, because it only took 75. Whereas in the previous notebook it took more than that. So yeah, it is 50. For 500 entities in the population, it took 795 seconds. With 50 entities in the initial population, it took 75 seconds. With the final population being somewhere about 70, initial population times 1.4, which I allowed it to expand a bit. So anyway, here's the plot. Same thing. So nothing unusual there. Let's see. Let's look at the previous one. See how they oscillate less if we have more entities if the population is bigger. But if the population is 10 times smaller, for instance, in this case, the plots for the heads, which is the blue line, the orange, which is the top 10%, green one top 20%, red one the tails, they just go up and down by bigger, by by bigger differences. They oscillate bigger. Their waves are bigger, and overall, their level is quite low, or rather lower. Because here, when we had a population of 500, the heads used to be very close to 700, whereas here, the highest one isn't that close. It's further away from 700 or 710 from this. So obviously, smaller population is well, I can say that it's almost, almost for sure, with certainty, say that a smaller population, or rather small populations, are not beneficial. That is the kindest way of saying it. Evolve it for a very long time, but with 50 entities in the population, so that took 25 seconds. So let me just check. 269 seconds, so that sounds about right. So again, 50 entities in the population, and if we look at the assessment, the heads, the tails, the top 10, the top 20%, they oscillate a lot, whereas if you look at here, they don't oscillate that much. So same impact, very similar impact with as seen in step 1 and as seen in step 2. Even when we evolve it for a very long time in one go, the same, we see the same behavior when that we saw from evolving it multiple times, but for different numbers of generations, one after the other, after resetting. So that's that. Number 3 is recording for every generation, for 3,000 generations, but for 50 entities. And here is the distribution. So you can see that because there are only 50 entities, the distribution isn't, it kind of looks like a normal distribution, bell curve, but it's barely that. It's not really pronounced, because this is 1 and this is 3. So not a lot of difference. You could almost say that these long bars are just outliers, and then you just have a uniform distribution, even distribution. So same, we see that it's oscillating. 50 for heads until generation 50, generation 150 for heads. They're not even like with this small population, the heads aren't even reaching the 700 level consistently. They're just there, and then they just go down, and then they come up, and they just go down. And then for the top 10%, again, we don't see that much of a plateau because they oscillate so much. And again, they're not as the overall level at which they oscillate around is still lower than here, for instance. This is the same thing. They're more unstable. If you follow this red line, it just went up here, came up to here, and then goes down, goes down, goes down, and then goes back up, and then goes down. Whereas for 500 entities in the population, they go up and they come down, and then they just stay there. I mean, we can still see the dip with this cyan line, this light blue, and this light blue as well. But with a smaller population, with small populations, the dip doesn't happen, but not in a good way. The dip doesn't happen because the entire population just goes through some kind of a turmoil, and the summed utility values just fluctuate too much, and then they lose information. Because if you lose one entity that used to be kind of high, that's 2% of the population gone, whereas if you lose one here, that's 0.2%, so that's really small, of course, 10 times. And until generation 300 for heads, even when we do have only the heads illustrated here, for until generation 300, we don't see the heads constantly hitting 700 or 710, anywhere close to 700. No, they just fluctuate too much. They just oscillate on and on and on and on. So very unstable. Until generation 300 for the top 10% entities, same thing. It just goes up and then goes down, and so this is very unstable. So apparently 50 entities for the initial population, and at most 70 entities at most, is not a good idea. So the last ultimate step in this case is to evolve, but with different numbers for the population size, starting from 50 to 2000. I mean, before it used to be 3000, but 2000 should be fine. And again, obviously, all the metrics will have to be saved separately in this case. Well, mostly for me, because I find, at least now, right now, I find this easier to keep track of. But there would be some other better ways, much better ways of doing this, but this will do for now. So, yep, keep the scores per, grouped by the number of, the population size for 10, 50, 100, 150, all the way down, all the way up to 1000. Well, I do skip some numbers, but 1000, and then right all the way up to 2000. So right to straight up to, from 1000 right up to 2000. So double there. So in this case, I kept track of three values, three assessment metrics: heads, the top 10%, and the tails. I left out the top 20% in this case. And the population size goes from 10, 50, 100, 150, 200, 250, 300, 350, 400, 450, 500, and then 600, 700, 800, 900, 1000, 2000. So there are 17 different population sizes, and if I run this, it will take about 2100 seconds. So on Google Colab, it's going to take me 8000 seconds, about 140 minutes, 120 to 130 minutes. So I'm not going to do that here. I don't want to edit anything. I think one day I have to film this while I'm doing it, and on my Mac, so that I can do more of these recordings while running the cells. Yeah, more to the live spectrum. So, and this is the assessment. This is the plot for everything for the heads. Very hard to decipher, but there we go. This is for the top 10%. So slightly less with the same frame. So max being 50. I mean the maximum for the y-axis being 750, and the red line indicating 710. And so this is all very expected. As of now, we don't know which lines here are for which population size. So for that, we move on to this. This plot tells us, tells us exactly that. So the black one, well, I'll start with the biggest population size. The black line is for population 2000. And you can see that it quickly reaches the best possible summed utility value, which is 710, and just stays there. So there's per generation there's always one or two, there's more than one entity around 705 or 710. And this one, the blue line, is for when the population size is 50, and as you can see, it oscillates a lot, as we've seen here. And anything above that are bigger populations. So for example, this is 100, 150, 200. So this orange line should be 200. This is somewhere like 300. This is probably 900. This red one, I think, or this brown one, it's hard to see. So the bigger the population, the more stable the head entities get. I mean, some of them will die out, but overall the score for this. And this is the plot for the top 10%. Again, the black one is when the population size is 2000. If you look closely, there's an orange peak here. That is very odd. I don't know how that happened. It's probably one of the first times. It's probably one of the very few times I see this. And there's another blue peak here. But overall, the top 10%, the average of summed utility values for the top 10% entities, again, seem to be higher and more stabilized as the population size goes up. And again, the blue one is for population 50, pop size 50. You can see that the sizes of the oscillations get smaller as the population size gets bigger, as well as their oscillation level, or at which the level of the metric that they oscillate around also is raised as the population size increases. But one sad thing to note is that ever since it, the moment it peaks and then sort of plateaus, none of them actually go up in a steady fashion, except these rare occasions. They all just stay at that level. This is for the tail. So this is again expected. However, this was not expected. But now that I think about it, this is also obvious. The tail entities will have much lower values that oscillate less, but still lower than others, because of the sheer size of its population, their population size, which is 2000. So, and if you think about it, if you have more entities within the population, the smallest, the lowest of them, the lowest of these scores would tend to be lower than their counterparts who are in smaller populations. So the bigger the population, the more likely it is for you to have higher summed utility values and also lower summed utility values. So that's what this illustrates. This is the so far I think this is the only downside, apart from taking longer to compute, taking longer to evolve, but this is the only downside to having a bigger population. So let's zoom in a bit, and zooming in until generation 150. This is for the heads. You can see that the black one is for population size 2000, just stays there, and everything else where the pop sizes are smaller than 2000, they oscillate a lot more, whereas the black line, it just stays there. And we're not even using the procreate function, the Lonely Island procreate function, where the top entity per generation gets to survive, no questions asked, by replicating itself or being passed on in its entirety. But that's not the case here. But even considering that, the black line just stays there. Sometimes it's 705 or 700, sometimes it's 710, but it's still there. And again, the lower ones indicate smaller population sizes. This is for the tail. Again, like I've said, bigger population means more occurrences of entities with possibly lower summed utility values, or lower scores of some kind, whatever we're trying to measure. This is for top 10%. So for the red, for the black, which is for population 2000, population size 2000, it plateaued, it climbs up, and then it stays there. There's not much of a plateau, not much of a peak, as it just generally goes up. For the red one, there is a peak, and then it comes down, and this is for smaller population. Same story for the brown one, same story for the orange one, and they are all more sort of volatile, as they just fluctuate more. Same word. They're more volatile because the differences between the these ups and downs are bigger. Whereas for the black one, they're quite stable. They go up, comes down a bit, but there's the differences are very small compared to the other ones. The blue line is for population 50, population size 50, pop size 50, and it is terrible. So that's about it for this notebook. And in my next video, I'll probably cover. I'll try covering grid search 3 for 40 items and for 50 items. Yeah, that's it. See you next time. Bye.